Welcome to the lecture about geomechanics. My name is Eduard Ziganshin. As the subtitle of the course indicates, it's about combining knowledge of the stresses in the earth, the forces in the earth, with the principles of rocks mechanics. We will use structural geology, we'll use petroleum engineering, we'll use earthquake seismology. We're going to integrate a lot of these different fields to address a number of problems of direct relevance to oil and gas reservoirs. The term geomechanics is sort of a new term. It's kind of become popular in the last few years. It means different things to different people. What it means to me is this integration of knowledge, quantitative knowledge of forces in the earth, quantitative knowledge of the physical properties and characterization of the earth, to then solve problems of practical importance. So I want to give you an idea of what we're going to cover and where we're going. Now, why is geomechanics important? Why has this field sort of developed over the last 10 to 15 years, coming from sort of nowhere? Well, in a real practical sense, if you're interested in drilling and reservoir engineering problems like compaction drive, subsidence, production-induced faulting, are or real problems people face every day. A parallel problem is optimizing drainage of fractured reservoirs. Many reservoirs around the world are fractured, and those fractures are essential to the production, and we need to understand those reservoirs in order to optimize production. Hydraulic fracture propagation is controlled by the stress field, and we'll talk about that. And obviously hydraulic fracturing has been important for a number of years, but has gotten increasingly more important with the development of unconventional resources where the matrix permeabilities are often in the scale of nanodarcies as opposed to millidarcies or even darcies. Well, bore stability is a huge problem that costs the industry literally billions of dollars a year lost time due to unstable wells. And it's geomechanics that helps us understand those problems and avoid them as subsequent wells are drilled. Anyway, a number of important problems related to drilling and reservoir engineering. On the more geologic and geophysical side, again, this is where fractures reservoirs are important. Pore pressure prediction is extremely important when we're in a sedimentary basin where pore pressure are elevated at depth. What I'll show you is it has a major control on the stress field. Pore pressure and stress are closely coupled, and when pore pressure is extremely high, it's very hard to drill because you have to balance the mud weight, the density of the drilling mud. Between the pore pressure, the drilling mud has to be higher than the pore pressure, so the well doesn't flow. But lower the density has to be sufficiently low than while it is greater than the pore pressure, it's less than the least principal stress. Because if the pressure exceeds the least principal stress, you will accidentally hydraulically fracture the well, and this is what's referred to the mud window. The same operating range of pressures between the pore pressure and the least principal stress. And we need to be able to predict pore pressure in advance of drilling, so you don't either have a blowout because your pressure are too low, or you have a collapsed well because you have fractured the well unintentionally, and all the drilling mud then disappears out the fracture, and then suddenly the well collapses. Okay, a number of other geologic problems are of interest. For example, fault seal integrity, understanding how reservoirs are compartmentalized, understanding hydrocarbon migration. You know the buoyancy of hydrocarbons, of course, is the main driving force for their movement. but exactly how they move, right? Are they moving through the matrix permeability of a given formation? Are they moving along conduits, fractures, and faults? Under what conditions is what migration sort of a dynamic process and interplay between pressure and containment by either the fault or the hydraulic fracture? And compartmentalization is a big deal. Imagine that you are working for oil company. You have identified a reservoir. You've mapped faults in the reservoir. Are those faults compartmentalizing the reservoir such that you need to drill a well in each one of the compartments, one or more wells to produce the hydrocarbons, or will there be fluid flow across the faults and you need further wells? Well, we have some ideas about how to predict that. Of course, for about the last 10 years, we're all aware of the shale gas revolution, the ability to drill horizontal wells and carry out multiple hydraulic fractures to produce initially natural gas from these extremely low permeability source rocks, right? The organic rich shales from which the hydrocarbons originally, were derived. And so we're producing natural gas directly from the source of, not from the reservoir, and our coming the extremely low matrix perm. Now that technology is being applied more broadly to Thai oil reservoirs, and so what's happening now around the world is horizontal drilling and multi-stage hydraulic fracturing are being used. The vertical stress is the result of the weight of the overlying rock. We can learn about the weight of the overlying rock from something like a density log, which are routinely collected. One of the way of proselytizing about geomechanics has been to consider describing a reservoir geomechanically like describing a reservoir geologically, or describing a reservoir with respect to its flow properties for reservoir simulation. But instead now we're going to try to describe it geomechanically, which means building a geomechanical model. And I want to show you what the components of that model are here in just a second. And the purpose of this slide is to put the process of oil and gas development in sort of a historical framework and think about geomechanics in the same framework. So, for example, you start with exploration. Suppose you find a reservoir. You need to appraise the reservoir. You do more drilling. You find out that the potential resource is like, and then you develop a development plan, and you start drilling and producing the hydrocarbons through what's called harvest. And then you, as production declines, you go through various secondary and perhaps even tertiary recovery techniques, and finally you abandon the reservoir. Through that life cycle, which will take, of course, decades, a lot of problems arise. For example, poor pressure prediction and wellbore stability are problems that you have to face early on. You don't want your wells blowing out, you don't want your wells collapsing. As you appraise the reservoir and start to develop it, you start to ask yourself questions about fault seals and compartmentalization. How many wells are you going to need, as you in other types of reservoirs? You might be very interested in what fractures are present. What do they mean for permeability and isotropy in your development here? In other reservoirs, perhaps there are very weak sands or weak chalks, and you're very concerned about how much you can produce a reservoir without causing irrevocable change in the reservoir properties, depletion-related compaction. And the point that I emphasize again with thought of a religious fervor, that in the well that are drilled in the very first part of the exploration process, you have the ability to build a geomechanical model. And you can then use the geomechanical model through the lifetime of the reservoir to solve this problem as they arise. You don't have to build that model over and over again, but of course your model will be a lot better as you go along. That it's initially you'll have more limited data at the first part of the process than along the way, but it's a very tractable problem. All the things that we're going to talk about, whether if the rock properties of the fractures or the stress are going to vary from place to place, but they're going to vary in sort of a coherent way. And what we're going to start doing is building that model early on, and then we're going to test that model as the drilling goes on and refine that model. But nonetheless, you can start very early and take advantage of that. There is no point in struggling with problems of wellbore stability for dozens and dozens of wells, and then finally, say a wellbore collapses and you lose everything for that practically. Well then, in fact, the very first well you drilled contained the information you need to avoid those problems subsequently. So that's sort of a philosophy underlying all of this, and that's why we're going to have you actually build a geomechanical model using the kinds of data that are rationally available. So the stresses are important. Typically, when we talk about the stress field, we're really talking about the three principal stresses which are normally acting in a vertical and horizontal plane. We refer to those stresses as SV, the vertical stresses, the overburden, the maximum horizontal stress and minimum horizontal stress. Three principal stresses. And then to orient that we need to angle which is the orientation of the stresses in that horizontal plane, and that orientation is usually the azimuth of the maximum horizontal stress. So for parameters describe the stresses field, and I'll explain the theoretical basis for that in the next time. Stress is a second order tensor. It has 9 components. It can be in any arbitrary coordinate system. 6 of those components are independent, but nonetheless. Of course, we need to know the pore pressure, we need to know the rock properties, and here we're referring to the rock strength, but they often need other rock properties, obviously, for other applications. And we need to know something about the fractures and the faults. We can see larger faults with 3D seismic data, and with good data we can see relatively small faults, but we don't see them all. And we use image logs which are now widely available to look at the smaller scale fractures and faults, and we can actually sometimes see faults of interest in core samples, etc. And we're going to kind of combine all this in different ways to solve a given problem as they arise. So with respect to the tectonic stress field, we have to recognize that geologic processes are responsible for the stress field, and it was recognized in the 1930s by British geologist by the name of Anderson that in general you can classify the forces, the stress fields in the Earth, into 3 major categories. He calls one category normal faulting. Of course, the second category, a more compressive stress state, is strike-slip faulting, and the most compressive stress state is reverse faulting. And what Anderson did, and his real insight, was to recognize that the relative magnitudes of these 3 principal stresses are changing in each of these stress fields. And the way to keep track of all of this, to keep your eye on the vertical stress in the normal faulting domain, the vertical stress is the largest of the 3 principal stresses, and if faulting is going to occur, it's going to be an extensional fault, a normal fault, which strikes in the direction of the maximum horizontal stress, and the slip on that fault is in the opposite direction, in the direction of the minimum horizontal stress. And he called this normal faulting because he was studying coal mines in the UK, and when the mine would normally hit a fault, they would find the coal on the other side, below them, and that would be a normal fault. Where what's called the hedging wall moves down with respect to the foot wall of the fault. So in a normal faulting stress state, the vertical stress is the maximum stress. The maximum horizontal stress is the intermediate stress, and the minimum horizontal stress is the least principal stress. A compressive force is a positive force. Now that is the standard convention in structural geology. It's a standard convention in rock mechanics. It's not the standard convention in material science, and when our colleagues in material science are studying the failure of materials, failure of is much more prevalent and prominent when the materials are in extension. But what is important to us is the fact that compression is a positive stress, and the stresses in the earth are always compressive. In fact, the stresses in the earth are always such that in this case, the minimal horizontal stress is greater than the pore pressure. Now, the pore pressure in an open system, as well see, is just the weight of the water above a depth of interest, and the least principal stress always has to be greater than the pore pressure, or the earth will sort of self-hydrofrag, because the tensile strengths of rocks are very low. So the stress are always compressive, the stress are always positive, and the stress are always greater than the pore pressure. Now the next most compressive stress regime is strike-slip faulting. Now instead of the vertical stress being maximum, the vertical stress is the intermediate stress. The maximum horizontal stress is greater than the vertical stress, which is greater than the minimum horizontal stress. If faulting occur, strike-slip faults are expected to be vertical and oriented about 13 degrees from the direction of maximum horizontal stress. We'll derive that, you'll see where number comes from. The most compressive stress state is where both horizontal stresses are greater than the vertical stress. This is called reverse faulting. If faults are active, those faults are dipping at about 13 degrees. They dip in the direction of the maximum horizontal stresses. And if you are understanding on that fault, the hanging wall of the rock above you are moving up with respect to those in the foot wall. So we have to, as we begin to study the stress field, we're going to first try to understand the vertical stress, which is of relevance for the depth we're interested in, and then we're going to try to understand the relative magnitudes of SH max and SH mean with respect to the vertical stress. Are they both smaller than the vertical stress? Are they both greater than the vertical stress? Is one greater and one less? And this is not an abstract concept. As a result, scientists are actively studying the distribution of stresses in the Earth's crust. The stress state maps are constructed on with the arrows show the direction of the main, maximum, and minimum horizontal stresses. This makes it possible to predict the behavior of the rock during an artificial change in the stress state of the rocks. Let's try in turn to determine all the necessary parameters to describe the stress state of the rocks. The first is the vertical stress. The magnitude of SV is equivalent to integration of rock densities from the surface to the depth of interest. Most clastic sedimentary rocks has an average density of about 2.3, which corresponds to a porosity of about 15%. This results in a vertical principal stress that increases with the depth at a rate for 23 megapascals per kilometer. Correspondingly, the magnitudes of the two horizontal principal stresses increase with depth. Some of the practical problems associated with the computation of SV relate to the facts that density logs frequently measure anomalously low density when the well is rugged. Various empirical equations are used to fill in the missing density logging data. Some of them are shown on the slide. For example, that is, we take an interval where there is a density logging record, build a dependence based on this data, and compare it with empirical equations. The most suitable equation is then used to fill in the missing gaps. The next step is to determine the direction of the horizontal stress. So how do we get our information about stress? We use the stress concentration around the vertical well. We'll go through the mathematics for this in great detail, but basically the way to think about it, we're going to go through it all for a vertical well, where on principal stress is vertical. That is sort of the normal case, where one principal stress is vertical. Vertical wells are ubiquitous, but we're going to generalize it for the general case of any operations of any well, and in fact any orientation of any stress fields, which is an unusual case, but a case we'll talk about in the next time. For a vertical well, where on principal stress is vertical, the hoop stress, the stress that acts sort of in parallel to the circumference of the well. This hoop stress varies sinusoidally around the well, such that in this case, if we have SHMax operating in sort of a north-south direction, we see a very strong compressive hoop stress 90 degrees from the direction of SHMax, which can lead to wellbore failure, compressive failure of the rocks, and these are called breakouts. The rock here fails out during the drilling process. Under some conditions, this hoop stress can actually become negative and the rock can actually fail in tension. These are called drilling-induced tensile fractures, and this can also occur during normal drilling operations. Now, because the stress concentration is related to the orientation of stresses, if we know the orientation of the breakout, or we know the orientation of the drilling-induced tensile fractures, we know the orientation of the stress state. We also know that the stress concentration here was enough to exceed the strength of the rock. So just by recognizing that these failures of the rocks have occurred, we're beginning to get a lot of information about the stress fields just by looking at the well. And here's what looking at the well means. Now on the left is what's called a UB logs. It's an ultrasonic scan of the wellbore wall. So this is a few meters of depth, and we go around the wall from north around the well, north, east, south, west, and north. And here we make a cross section of the well from these little acoustic pulses that have been bounced off the wall. And we can in fact see the breakout here, which corresponds of these dark zones here where the acoustic pulse is scattered. And immediately we know that the SHMax direction is like that. Okay, now this is an electrical image log. I'll talk about this more. It's Schlumberger, one of the service companies, refer to these logs as FMI logs. It's basically an array of electrodes that is pushed against the wellbore wall. You can see the results of these breakouts occurring, and again it gives you an idea of SHMax. Those drilling-induced tensile fractures, which you can see in the cross-section here, are giving the independent indicators of the direction. And again, it's telling us that the hoop stress actually got down into tensile failure mode, and that the compressive stress got into a mode where we're actually exceeding the stress of the rocks. Just by looking at the well, we're learning a lot about the relationship between stress in the earth and the rock properties. Traditionally, most of the data used to determine the orientation of breakouts in wells come from magnetically oriented 4-arm caliper data, which are part of the deep metal lodging tool that is commonly used in the petroleum industry. Despite the relatively low sensitivity of this technique, with sufficient care, it is possible to use 4-arm caliper data to reliably determine breakout orientations. While the analysis of wellbore breakouts with 4-arm caliper data appears to be quite straightforward, it is important not to misinterpret K-seeds, growth in the site of the well caused by the rubbing of pipe, or washouts, enlargements of the inter-wellbore circumference, as stress-induced breakouts. In fact, relatively little information comes from a standard deep metal log. The diameter of the well, as measured by the orthogonal pairs of caliper arms, termed the C13 and C24 pairs, as the arms are numbered sequentially looking down the hole. The pad 1 azimuth, the deviation of the well, and the hole azimuth. The actual resistivity data measured on each pad are not used in the breakout analysis. Breakouts are wellbore enlargements caused by stress-induced failure of a well occurring 118 apart. In vertical wells, breakouts occur at the azimuth of minimum horizontal stress (SH mean) and generally, when analyzed properly, show a remarkably consistent orientation within a given well or field. One pair of caliper arms measures the size of the drill bit, whereas the orthogonal pair measures a larger diameter. The lodging tool doesn't rotate with depth in the breakouts. Washouts represents essentially complete failure of the wellbore such that both sets of arms of the 4-arm caliper are larger than the diameter of the drill bit. K-seeds are an asymmetrical notching of the well caused by mechanical wear of the borehole at its top or bottom, or on the side of the well if there is a rapid turn in the well trajectory. It is also useful to use a wellbore deviation criterion to help distinguish K-seeds from breakouts. Even in near vertical wells, great care needs to be taken when considering enlargements of the wellbore that are essentially parallel within 10-15 degrees to the well deviation direction as indicators of wellbore breakouts. Another way to determine the direction of stresses is cross-dipole sonic lodging. If we have a large difference between the maximum and minimum horizontal stresses, then fracturing will be observed in the rock mass, and this causes anisotropy. Thanks to cross-dipole sonic lodging, we can capture the direction of fast and slow waves. The direction of propagation of the fast wave corresponds to the direction of the cracks. Therefore, this direction corresponds to the maximum horizontal stress. Now we should talk about determining the minimum horizontal stress. In this section, we consider two fundamental aspects of hydraulic fracture initiation and propagation that were addressed in a classic paper by Hubert and Willis. The way in which the stress concentration around a well affects the initiation of hydraulic fractures at the wellbore well, and the manner in which the orientation of the minimum principal stress away from the well controls the orientation of a hydraulic fracture as it propagates. Hubert and Willis presented a compelling physical argument that hydraulic fractures in the earth will always propagate perpendicular to the orientation of the least principal stress S3. Because the work done to open a mold fracture a given amount is proportional to the product of the stress acting perpendicular to the fracture plane times the amount of opening, hydraulic fractures will always propagate perpendicular to the least principal stress because it is the least energy configuration. They confirmed this with simple sandbox laboratory tests and pointed out that igneous dike propagation is also controlled by the orientation of the least principal stress. This fundamental point is the basis for using hydraulic fracturing to measure the magnitude of the least principal stress as discussed below. A schematic pressure time history illustrating an X-slot leak-off test or mini-frac is shown in figure. In the schematic example shown in figure, the pumping rate into the well is constant. Thus, the pressure should increase linearly with time as the volume of the wellbore is fixed. At the pressure where there is a distinct departure from a linear increase of wellbore pressure with time, referred to as the LOP, the leak-off point, a hydraulic fracture must have formed. The reason for this is that there cannot be a noticeable decrease in the rate of wellbore pressurization unless there is a significant increase in the volume of the system into which the injection is occurring. In other words, the pressure in the wellbore must be sufficient to propagate the fracture far enough from the wellbore to increase system volume enough to affect the rate of wellbore pressurization. Thus, there must be a hydraulic fracture propagating away from the wellbore perpendicular to the least principal stress in the near wellbore region. When there is a noticeable change in the pressurization rate. Thus, a clear LOP, a distinct break in slope, is approximately equal to the least principal stress. Although the wellbore pressure may also reflect some near wellbore resistance to fracture propagation, if the hydrofrac is being made through perforations in a cased and cemented wellbore, as is the case in mini or microfracs, the tortuosity of the perforation fracture system may cause the pressure to increase in the wellbore above the least principal stress. The same is true if the injection rate is high or if a relatively high viscosity fluid is used. It should be noted that figure represents pressure at the surface during a mini-fracs or leak-off test, not that the pressure is zero at the beginning of the test. To determine the magnitude of the least principal stress at the depth of the test, it is necessary to add the pressure in the wellbore due to the column of wellbore fluid. In fact, it is always preferable to measure pressure downhole during such tests. If the LOP is not reached, a limit test or formation integrity test is said to have been conducted. Such tests merely indicate that at the maximum pressure achieved, the fluid pressure didn't propagate away from the wellbore wall, either because the minimum wellbore pressure didn't exceed the least principal stress or was not sufficient to initiate a fracture of the wellbore wall in the case of an open hole test. The peak pressure reached during a leak-off test or mini-frac is termed the formation breakdown pressure, FBP, and represents the pressure at which unstable fracture propagation away from a wellbore occurs. Fluid flows into the fracture faster from the wellbore than the pump applies it, hence the pressure drops. The difference between the LOP and FBP is a complex function of the conditions immediately surrounding the well, especially when a frac is being initiated through perforations. If pumping continues at a constant rate, the pumping pressure will drop after the FBP to a relatively constant value called the fracture propagation pressure, FPP. This is the pressure associated with propagating the fracture away from the well. In the absence of appreciable near wellbore resistance mentioned above, if the flow rate and fluid viscosity are low enough, the FPP is very close to the least principal stress. Hence, the FPP and LOP values should be similar. It should be emphasized that the distinct FBP need not be present in a reliable mini-frac or XLOT. This correspondence between the LOP and FPP is the reason why in typical oil field practice leak-off tests are taken only to the LOP rather than performing a complete extended leak-off test. An even better measure of the least principal stress is obtained from the instantaneous shooting pressure, ISIP, which is measured after abruptly stopping flow into the well, because any pressure associated with friction due to viscous pressure losses disappears. In carefully conducted tests, constant and low flow rates, 200 liters per minute, are mentioned and low viscosity fluid is used and pressure is continuously measured. In such tests, the LOP, FPP, and ISIP have approximately the same values and can provide redundant and reliable information about the magnitude of S3. If a viscous frac fluid is used or a frac fluid with suspended propant, FPP will increase due to large friction losses. In such cases, the fracture closure pressure FCP is a better measure of the least principal stress. Pore pressure. Pore pressure at depth is of central importance in reservoir geomechanics. As illustrated in figure, pore pressure is defined as a scalar hydraulic potential acting within an interconnected pore space at depth. The value of pore pressure at depth is usually described in relation to hydrostatic or normal pressure, the pressure associated with a column of water from the surface to the depth of interest. Hydrostatic pore pressure increases with the depth at the rate of 10 megapascals per kilometer. Hydrostatic pore pressure implies an open and interconnected pore and fracture network from the Earth's surface to depths of measurement. Next figure shows that variation of pore pressure with depth from observation in the Monte Cristo field along the Texas Gulf Coast by the Mark Zobak. The way in which pore pressure varies with depth in this field is similar to what is seen throughout the Gulf of Mexico oil and gas province and many sedimentary basins where overpressure is encountered at depth. At relatively shallow depth, in this case to about 800 feet, pore pressure are essentially hydrostatic, implying that a continuous interconnected column of pore fluid extends from the surface to that depth. Between 8,000 feet and 11,000 feet, pore pressure increases with the depths very rapidly, indicating that these formations are hydraulically isolated from shallower depth. By 11,000 feet, pore pressures reach values closer to that of the overburden stress, a condition sometimes referred to as hard overpressure. Now consider the experiment that was carried out by the scientist Terzaghi. Soil was poured into a steel cylinder and filled with water. Both cylinders were loaded with a piston. In first case, water was filtered, that is, water could easily leave the rock. In case 2, the valves were closed and the water didn't go anywhere. In third case, the water left the ground and the ground was deformed. In case 2, the water remained in the soil and the soil didn't deform. Let's look at both cases. In the first case, the water pressure was constant and the load increased. In the second case, the water pressure increased with the load. This resulted in the effective overburden pressure being derived. In the context of the cartoon shown in the figure, it's relatively straightforward to see that the stresses acting on individual grains result from the difference between the externally applied normal stresses and the internal fluid pressure. If one considers the force acting at a single grain constant, for example, all of the force acting on the grain is transmitted to the grain contact. And thus the force balance is Ft equal Fg, which in terms of stress and area can be expressed as the next, where AC is the contact area of the grain and sigma c is the effective normal stress acting on the grain contact. Introducing the parameter A equal AC divided AT, this is written as next. The intergranular stress can be obtained by taking the limit where A becomes vanishingly small, such that the effective stress acting on individual grains sigma g is given by next, for very small contract areas, of course. It is clear in figure that pore fluid pressure doesn't affect shear stress components. So, if you think about the vertical stress being the maximum stress, as it is in the diagram on the left, and the true horizontal stress being lower, and we have the pore pressure showing by the dotted line, you can make some very crude estimates of what stress magnitudes are. Okay, the vertical stress goes up in sedimentary basins at about 23 megapascals per kilometer. That for a density of rock about 2.3, which is a normal sedimentary rock with something like 15% porosity. If pore pressure is hydrostatic, the pore pressure is going up by 10 megapascals per kilometer, or about 0.44 psi per foot. And in a normal faulting regime, the vertical stress, the pore pressure, and then we have the minimum horizontal stress and the maximum horizontal stress intermediate between the two, defining the stress state. If we are in a strike-slip faulting regime, then the minimum horizontal stress is less than the vertical stress and the maximum horizontal stress is greater than the vertical stress. And if we're in a reverse faulting regime, both horizontal stress can be larger. In fact, there is not enough room on the graph. Both horizontal stresses can actually be quite large, and we'll talk about that later. So just knowing something about the relative stress state begins to give us a sense of what the stress magnitudes are. We know very little at this point. We know it's a normal faulting regime, and yet suddenly we know that at a depth of, well, let's say 3000 meters, we know that the overburden is, 3 times 23, that's 69 megapascals. And the true horizontal stresses are less than that, and the mean stress is, something like maybe 50, 60 megapascals. The question is whether or not the relative stress magnitudes change a function of depth, and in general they don't, but we have seen instances in which they do. The point of this is to integrate these concepts over many different depths, but in general you're going to be interested in a limited range of depth also, and you want to be able to characterize the relative stress at those depths. Where this is most concern is when we're using earthquakes to kind of inform us about the relative stress state, because often reservoirs are at depths of 2, 3, 4 kilometers, and the earthquakes might be at 5 or 10 kilometers. So when we're using earthquakes as an indicators for relative stress magnitudes, we have to pay very close attention to that questions. When the pore pressure is elevated at depths, which is shown schematically here, within near hydrostatic pore pressure at shallow depths for our normal strike slip and reverse faulting cases, and near lithostatic pore pressure. As the pore pressure goes up and becomes close to the overburden that you see is because the least principal stress has to be greater than the pore pressure in a normal faulting regime. The maximum horizontal stress is greater than the minimum horizontal stress, and the vertical stress is the maximum. Look what happens. We have almost an isotropic stress state. It's still normal faulting, vertical stress is still largest, the minimum stress is still bigger than the pore pressure, but there's very small differences between the three principal stresses. Remember I said how different normal faulting and reverse faulting were when I showed the hydrostatic pressure version of the same slide. Now when we look at it, we see a near hydrostatic stress state here, near isotropic stress state in both cases. So as pore pressure gets elevated, the stress field becomes more uniform. The basic principles are the same. SH max is still greater than SH mean, which is still greater than SV, but at very elevated pore pressure, as well as C in this case, the frictional strength of the crust is so low that it can't sustain big stress differences. And is so the difference between normal faulting and reverse faulting, which is just huge from a stress magnitude perspective at great depth when we compare normal faulting and reverse faulting. When pore pressure are severely overpressured, when pore pressure is very high, then different sorts of disappear. In fact, when we start talking about the world wellbore stability problem, wellbore stability means getting the stress right and getting the rock strength right in a hydrostatic pressure regime, because the stress difference can be quite large. If you're drilling in an overburden area, wellbore stability kind of means estimating the pore pressure right and getting that mood weight to fit in that mood window. So it's really a very different environment, and so stress and pressure are very closely coupled. On a real or imaginary plane, through a material, there can be normal forces and shear forces. Furthermore, it should be remembered that a solid can sustain such a shear force, whereas a liquid or gas cannot. A liquid or gas contains a pressure, a force per unit area, which acts equally in all directions and hence in a scalar quantity. The normal and shear stress components are the normal and shear forces per unit area. Strain is a change in the relative configuration of points within a solid. In order to provide a structure for our analysis of two-dimensional strain, we'll consider the separate components of strain. There are normal strains and shear strains, and illustrated in figure. As with normal stress and shear stress components, it is much easier to grasp the concept of normal strain and shear strain. This is because the normal displacement and the associated strain occur along one axis. However, in the case of shear strain, the quantity of strain also depends on the position along the y-axis. In other words, normal strain only involves one Cartesian axis, whereas shear strain involves two or three. It involves an interaction between the axes. The theory of linear elasticity deals with situations where there are linear relationships between applied stresses and resulting strains. While most rocks do behave non-linearly when subject to large stresses, their behavior may normally be described by linear relations for sufficiently small change in stress. Consider a sample of length L and cross-section area A when the force F is applied on this end surface. the length of the sample is reduced, the applied stress is then sigma x equal F divided A, and the corresponding elongation according to equals. If the sample behaves linearly, there is a linear relation between sigma and between stress and strain, which we may write next. Equation is known as Hooke's law, while the coefficient E is called Young models or simply the E models. Young's models belongs to a group of coefficients called elastic modeling. It is a measure of the stiffness of the sample resistance against being compressed by a uniaxial stress. Another consequence of the applied stress is an increase in the width of sample. The lateral elongation is epsilon y equal epsilon z. Thus, epsilon y and epsilon z become negative, the ratio defined as next equation. With another elastic parameter, known as position ratio. It is a measure of lateral expansion relative to longitudinal contraction. Evaluation of in situ rock's mechanical behavior requires relevant input data. What is the stress state and the pore pressure at the depths of interest? What are the elastic moduli and the stress parameters? Can we expect creep or other types of non-elastic behavior to take place? Our main data sources in order to answer these questions are core materials and data recorded in the field, measurements while drilling, wireline logs, seismic data, and various well tests. The logs provide data recorded continuously versus depth, but do not measure directly the parameters that are needed for rock mechanical analysis. For instance, rock strengths cannot be measured from wireline logs. Strength estimators may, however, be given if a proper interpretation produced is applied. Cores provide a possibility for direct measurements of rock strength parameters and static elastic properties. Of a rock mechanical core analysis have to be designed according to the purpose of the investigation. If the objective is to predict reservoir compaction, then the test and testing producers may not be the same as, for instance, in a borehole stability study. Consideration also has to be given to the rock type which is going to be tested. Shales require both spatial preparation producers and special test procedures. In some cases, it may be useful to perform a set of simpler measurements which can be used as indicators of rock strength and stiffness. This can provide information at less cost, at less material consumption. The latter is particularly relevant if the core is in a poor state and larger test plugs cannot be prepared. If performed at the rig site, results may be available closer to real time. The central element of the test system is the triaxial cell. A triaxial cell contains the loading pistons which are pressed against the sample. The sample is surrounded by a sleeve which separates it from the confining fluid in the case of confined tests. The pistons should be made for a hard material or steel pistons having a minimum specified hardness. The surface should be ground and polished, and their flatness should be within 5 micrometers. The flatness of the pistons has an important effect on the test results. If the friction coefficient between the sample and the pistons is large enough to prevent radial expansion of the sample at the end faces, then this is equivalent to providing the material with an additional support. This will manifest itself as a length diameter effect, since the support of the end faces will give rise to a higher measured strength with a short than with a long sample. In rock testing for petroleum application, one may wish to have fluid inlet and outlet in the pistons in order to apply and measure pore pressure. This can be done by using sintered pistons or by introducing flow channels in the piston surfaces. The study of the elastic properties of rocks is important in geomechanics. Elastic waves are mechanical disturbances that propagate through a material. Such waves are able to travel over very long distances through the Earth and thus bring us information about parts of the formation that are otherwise inaccessible. In seismic surveys, elastic waves are generated at the surface, and the echoes from various layers in the formations below are used to map the structure of the underground. Earthquakes are generated by abrupt failure processes and propagate as elastic waves. Elastic waves in air and water are usually called acoustic waves or sound waves. These terms are often used about elastic waves in rocks too. Elastic waves in rocks propagate with a velocity that is given by elastic stiffness and the density of the rock. These parameters depend on other parameters such as porosity. Thus, elastic waves also provide a method by which specific formation parameters can be estimated in the field. The fact that elastic waves are mechanical disturbances means that there has to be a fundamental connection between rock acoustics and rock mechanics. This concludes the lecture on geomechanics. Thank you all for your attention.